today we're going to continue our discussion of series. And remember in our exploration we did, you remember how we realized that sometimes it fit pretty well on certain intervals and other times it didn't fit very well on other intervals? So that's what we're going to be looking at today, is the convergence of what's called a power series, but in general the convergence of a series. And there are a lot of different tests for that, so this will be a multi-day discussion. The first couple examples are actually continuations from Thursday, Friday, whatever we last spoke. Friday, right? Okay, so suppose f has derivatives of all orders at x equals 1. Suppose that the following values apply. F of 1 is 3, f prime of 1 is 4, f double prime of 1 is negative 8, f triple prime is negative 7, and the fourth derivative at 1 is 7. Write the fourth degree Taylor polynomial approximation centered at 1. So which formula are we using to write this? Good. So we are using Taylor series, not at 0, the x minus a thing that we have there. So the fourth, and the notation for that, as you probably figured out on the homework, is the fourth degree polynomial. 3 is first. Plus or minus, since it's negative 8. X minus 1 squared over plus. So what's the only difference, really?
You're just putting in the x minus 1.
Instead of just x, it's x minus 1 in parentheses at each term.
Where did you get x minus 1?
We are centered at 1. So you see how it says centered at A?
So it's x minus c.
Are you looking at notes or are you looking at... Does it say centered at 1 or centered at 0? So x minus a, you're looking at a different paper than
It's f prime of a. Think of it like this, Joseph. Normally it would be x minus 0. X minus 0 would be.
Let's see what you're looking at. Are you looking at the stuff you must know?
So, is it just that this is going to be an x minus 1 here? Because it doesn't have it here.
Oh, yes. There is a typo on that, isn't there?
Okay,
everyone, look. There's and this is very important information for you. On the packet that has the formulas, there's a typo. Now, in your notes, it was correct, but on the packet, the BC Calculus Stuff You Must Know packet, it's missing the minus a on just the first part. It's got it on all the others, but on the Taylor series generated at x equals a, on page, I don't know, series stuff, second box under series stuff. Yeah. I'll show you. Okay, everyone, see this page right here? This right here should have been an x minus a. See that highlighted spot? Should have been an x minus a. I didn't make that packet, I just printed it, so I didn't check it. Sorry. Times x minus a. On the other formula sheet, it's correct.
Yes. It is correct.
So on the other version of the formula sheet, it's good. And on the notes I gave you yesterday, it was good. I am glad you noticed that, Joseph. Thank you.
I was a bit lost.
Yes. I'm glad you were a bit lost so that you could let me know, because I would have never looked at that and known it was wrong. I just assumed that that was correct. Oh, and I lost effect. That's what I get for assuming, right? Okay, any questions about that one? Use this to approximate, and I am going to use a calculator just for time purposes. You could do it by hand because you'll just essentially be squaring 0.1 each time. But go ahead and give me the approximation of PF of 1.1. So P4 of 1.1 equals... What does it equal? Bless you.
About 3.35.
And that is an approximation for f of 1.1. Does everyone agree? So that might help. I think there were some on your homework that asked you to do that. That's how you do that. So now we've done one not centered at 0. Write the fourth degree Taylor polynomial to approximate cosine of x centered at pi over 4. So we have an approximation of cosine of x, but it's centered at 0. So it would approximate cosine really well close to 0, but instead I want an approximation of cosine close to pi over 4. I'm going to do this just using the Taylor polynomial formula. I'm not going to try to use my memorized formula. Is it? Almost a homework question.
It's asking for the fourth, it's not asking for the two.
So, the first thing I need is cosine of 0, or sorry, cosine of pi over 4. Oops. Then I need the derivative of cosine, which is negative sine at pi over 4. Then I need the derivative of that, which is negative cosine of pi over 4. For this approximation of cosine, is every other term going to go away? Like it did at centered at 0? Why not? The derivatives aren't 0, right? The reason at 0 every other term goes away on cosine and sine is because sine of 0 is 0. The derivative of cosine is sine. Am I going? So this is original, first derivative, second derivative, third derivative. I need fourth derivative, right? Is that correct? So I need one more. Probably would have been good if I labeled all those. Y prime at pi over 4. So my fourth degree Taylor polynomial, y is approximately radical 2 over 2 plus, or minus if you would rather, negative radical 2 over 2 times x minus pi over 4. plus, am I going too fast? Negative radical 2 over 2, x minus pi over 4 squared divided by 2 factorial. Plus radical 2 over 2, x minus pi over 4 cubed divided by 3 factorial, plus radical 2 over 2, x minus pi over 4 to the 4th power divided by 4 factorial. Did it ask me to do anything else? Just write the 4th degree. Okay. Any questions about that? This polynomial would better approximate if I were trying to approximate something close to pi over 4 compared to something close to 0. This one would do a better job. Okay, so today we're going to talk about testing for convergence of a polynomial. As you probably remember from the sequence review we did the first day, the sum of what's called a power series is just another word for a geometric series. Why do you think they call a geometric series a power series? Because it's multiplying, so you've got those powers in it. So they, in calculus, for some reason, they quit calling it a geometric series, start calling it a power series. Is a good approximation only on the interval of convergence. We need to develop some tools to find that interval. Remember, on a normal geometric sequence, r has to stay between -1 and 1. Do you know what I'm talking about? So we're going to talk about that. We're always going to check the interior first, and then we'll check the endpoints. We probably will not get to endpoint convergence today. We'll talk about that later, probably tomorrow. There are several useful tests. Each test has conditions that must be checked before it can be applied. These tests are a lot to remember, so they will be things that we have on our gateway exam as well, because part of the challenge is remembering what tests to use and where, so this will be something that shows up on your gateway exam as well. Yes. The first test is called the nth term test. I'm going to call it the American Idol test. It gets rid of the really bad ones. You know those really bad people on American Idol? Like the really bad ones? Okay. This is the really bad ones. If this sequence doesn't converge, okay, what that means, if I'm not even talking about a sum, and I'm just talking about the numbers in the sequence, if that doesn't go to 0, then there's no way for the sum of the sequence to go to 0, or to add to be anything. So if the numbers in the sequence, if that limit doesn't equal 0, or it doesn't exist, then there's no way for this series. Remember, a sequence is just a sequence of numbers. Series is the sum of that. So example, 1, 2, 3, 4. Okay, what's the pattern there? Adding 1 every time. What's the limit as n approaches infinity of that? Infinity, or does not exist, right? Is there any way I can add that up? No. It's going to be infinity, right? So if the limit of the sequence doesn't go to 0, there's no way I can find a sum. And this is called the nth term test for convergence, or really for divergence is what you're talking about. Now, if the nth term test doesn't work, it doesn't necessarily mean it converges, because there are some that would have a limit that approaching 0 that don't converge. But again, it gets rid of the really bad ones, the ones that we go, there is no way I could find a sum of that.
Is the top one F, any the bottom one F?
What?
That's for the derivatives, those functions. So F is K on that top row, that one, is that a K?
Oh, yes. N equals K to infinity.
And that bottom one is N equals 1 to infinity.
Yes. So I want to know if this could be convergent. What is the limit as n approaches infinity of n minus 1 over n plus 1? There is one. There is a limit. 1 by 1. Same degree, so we're putting ourselves back in chapter 1. Whoa, that was a flashback a long time ago. Right, they have the same degree, so that limit is 1. It's not 0. What does that mean? Diverges. So determine if that could converge. No, because the limit of this sequence is 1. What that means is the numbers get really, really big. These numbers go to 1. Well, what happens if you add up 1 infinitely many times? It goes to infinity, right? It does not converge to a number. If that limit is anything besides 0, it can't converge. So that's called the nth term test. Again, it just gets rid of the really bad ones. The next one is the geometric series test. A normal geometric series converges only if r is between -1 and 1. If it does, then we can find the sum using that formula we learned on the very first day. Quick mental note. If r is greater than 1, would it pass the nth term test? It wouldn't, right? If r is greater than 1, so 2 to the x power as x approaches infinity, or 2 to the nth as n approaches infinity, would not be 0. So we kind of have a heads up that this won't work if r is greater than 1 by the nth term test. But the nth term test does not tell us that something converges. It just tells us if it diverges. It's the first round of American Idol, right? It just gets rid of the really bad people. Really bad series. This one actually tells us whether a geometric series converges or not. So I want to verify that this converges. Well, is it geometric? Is -3/5 between -1 and 1? So it does in fact converge. So it converges. And if this were justification on an AP exam, you'd say by geometric series. Because -3/5 is between -1 and 1. For a geometric series, they may ask us to go ahead and find the sum. What is the sum of an infinite geometric series? I think we wrote it this way on your notes from Algebra 2. It's right there as well. So if you haven't written it down, there it is. Except it doesn't say infinity, it just says So the sum of a geometric series, infinite geometric series. What's A1? Well, it says AK, but the first term, what is the first term of this sequence? -3/5. Does everyone agree? How'd you find that? Plug in 1 for n. Then we need R, which is also -3/5. Those are not always the same thing. If there were a number in front here, that would change the first term, which is -3/5 divided by 8/5. Am I going too fast on the fractions? 5's cancel and I get -3/8. So the sum is -3/8 using the formula from Algebra 2. So our first test, other than the nth term test, is the geometric series test. If a geometric series, use that. Next one is called a PSeries test. We looked at this a little bit when we looked at improper integrals. And this is kind of similar to the discussion with geometric series. Just for fun, if 1/n to the p is my series, couldn't I rewrite that as 1/n all raised to the p? Everyone agree with that? Two of these will be a little bit obvious. The or equal to takes a little bit more thought, and we actually did that when we did improper integrals because we had the same thing come up with improper integrals. Remember when we did integrals as n approaches infinity? Wouldn't an infinite series and an infinite integral have a lot of similarities to them? Because they're both sums. Okay, if p is greater than 1, like 2, right? Wouldn't this be a lot like 1/n squared? And as n approaches infinity, wouldn't it make sense that that would go to 0 and it would be possible for me to do for the integral to converge? If p is less than 1, like 1/2, right, and especially if we were negative, it would throw it to the numerator, right? So because of that, obviously negatives make perfect sense. The P-series test even goes a little farther than that, which you discovered this when we did improper integrals, but it's been a long time. If P is less than or equal to 1, it's guaranteed to diverge. The series is guaranteed to diverge. If 1/n to the p, if p is greater than 1, it's guaranteed to converge. Now, I want to remind you from integrals, why that works. Now, integrals are slightly different, but they have some similarities. If you have x to the 1/2 power, and you do an antiderivative of that, and you're going from 1 to infinity per se, when you get to the 3/2 power, right? And when I get to the 3/2 power, that's when I have infinity to the 3/2 power, and that diverges, right? What happens when I subtract 1 from something greater than 1? So if I had 1/2, or sorry, add 1, on the bottom, so say I had -3 on the bottom, what happens when I add 1 to that? It's still negative, so remember it converged because it was still negative, but anything less than or equal to 1, so if we're on the bottom, less than or equal to 1, it diverged. It's greater than when it converges. So let's look at the example. I have the sum, n equals 1 to infinity. My first step, what should my first step be? Rewrite it. What is n to the 1/2 power, or what is, sorry, I answered the question.
It has to be into the 3/2.
Does everyone agree with that?
3/2 is greater than 1.
3/2 is greater than 1, so this sum converges. Now, when you plug in a 1, it may not seem like it's going to, but then look what happens when I plug in a 2 and a 3 and a 4 and a 5. You see how those numbers keep getting smaller and smaller? This does pass the nth term test. Remember, the nth term test gives us a weed out test. It's like Cal 2. It's weed out class. Okay, so that one converges. If we were doing an AP justification, we would say by P-series test. We'll do one more test for the day. We have lots of examples to do, so right now we're kind of learning all the tests. I do not believe all these tests are on your AP stuff to know. Are they on the other one? I don't think they are. But we need to know them, unfortunately. Direct comparison test. This test is used when a known series is bigger than the given series. There are two ways we can use a direct comparison test. If we know a series is bigger than a divergent series, all the numbers in the series are bigger than a divergent series, then the series will diverge. If we know that in a series we have all the numbers smaller than a convergent series, then the other series must also converge. Kind of like this, y'all remember us talking about the sandwich theorem back in limits? That was a long time ago and we didn't spend a lot of time on it, but a ceiling function is another word for a top function. It's greater than the other function all the way across, so a ceiling sequence would be one that's greater. So if a sub n has no negative terms and b sub n is greater than it always, if b sub n converges, then a sub n also converges. Similarly, if a sub n has no negative terms and b sub n is smaller than a sub n all the time, and b sub n diverges, then a sub n must also diverge. This is called the direct comparison test.
And it has to be. You said it's on the board, but you said it has to be smaller all the time.
Yes. A ceiling function would be one that's, think about a ceiling in a building, it's always above, and a floor in a building, it's always below. Now, there are two sequences that we have for comparison purposes. We have a geometric sequence and we have a p-series. Let's look at this example down here. What does it look the most like? Looks the most like a p-series, but it's got the random +3, so I can't just use a p-series test. But would you agree if I add 3 to the bottom, that makes these terms smaller than... So would you agree 1 over n squared plus 3 is less than 1 over n squared? Always? Every term, 1 over n squared plus 3 is always less than 1 over n squared. We know that 1 over n squared converges by a p-series test. So this series would have to converge by direct comparison with a p-series test. So that's how that works. We'll work on that wording a little bit better tomorrow. Yeah, I'll go back to it. You see we have some more tests and then we have some more examples, a lot of them. I'm going to go ahead and give you the homework. You don't have to touch it yet if you don't want to. There's a book page and then there's 4 worksheets. Power Series worksheets 1 through 4. This homework, the 8 through 42 even, will probably be due on Wednesday if we finish tomorrow. This homework is due on Monday, all 4 of these worksheets. So if you want to get them, you can. Some of it you could already do because some of it will say write a power series, which is just a Taylor polynomial. So if you want those, you can get them, but you don't have to. What is due tomorrow? Taylor polynomials. So that's your first thing to work on is Taylor polynomials due tomorrow.